Okay, in this video we want to find and classify the critical values for f parentheses x comma y is equal to y cubed minus 6y squared minus 2x cubed minus 6x squared plus 48x plus 20. In the last two videos we went over the reference table for second derivative test, which we will be using to solve this problem. So let's get started. The first thing we want to do is get the first partial derivatives in terms of x and y. So fx is equal to, so we would get negative 6x squared. So negative 6x squared minus 12x plus 48. Then we need to get the first partial derivative in terms of y. So fy is equal to 3y squared minus 12y. Okay, next we will get the second partial derivatives in terms of x and y. So we can say fxx is equal to, so we would get negative 12x minus 12. Likewise, we need to get the second partial derivative in terms of y. So fyy is equal to 6y minus 12. And we also need to get fxy. So let me just write another color. fxy. So we will take the partial derivatives of this in terms of y, which there's no y, so it would simply be 0. So now we need to get the critical points. And we do that by factoring out the first partial derivative of x and y. So critical point. So this would be fx is equal to 0. So we would get negative 6x squared minus 12x plus 48 is equal to 0. So we can say that this is a negative 6x squared plus 2x minus 8 is equal to 0. And then we can factor out. So we can say negative 6 parentheses x, so we have negative 4 plus 2. And so our critical terms in terms of x would be x is equal to negative 4 and x is equal to x is equal to 2. Actually, I made a mistake when I factored. This would be positive 4 and we would have negative 2. And so our two critical points would be negative 4 and 2. So x would equal negative 4 and x would equal 2. Now we do the same thing for y. We need to get the critical point. So we can say fy is equal to 0. We say 3y squared minus 12y is equal to 0. We factor out 3y. So we can say 3y parentheses y minus 4 is equal to 0. So our critical point would be y is equal to 0, comma, y is equal to 4. So now we're pretty close to solving. So we will construct a table of critical points. Okay, so we will construct a table. This would be critical point. This would be our D, and that's fine. We can keep it as that, D, and this would be fxx, and this would be our conclusion. And so our critical point is 2, 0, 2, 4, and negative 4, 0, and negative 4, 4. So let's write this down. So we would get 2, 0, 2, 4, -4, 0, and -4, 4. I guess we can separate it out a little bit. Okay, and now we apply our reference. So we need to get D. And so D is equal to fxx times fyy minus fxy squared. And so our first point was 2, 0. So what I'm going to do is insert 2, 0 for this. And when I put 2, I would get -36. So this term right here would be -36. And I do the same thing for fyy. I plug in 2, 0, which would make just -12. So we have -36 times -12. And we set our negative fxy is 0, so 0 squared. So let's write this down. So for this problem, we had -36 times -12 minus 0 squared. This term right here would be negative times negative is positive, so it would be greater than 0. Our fxx was -36, so -36 is less than 0. And if you look at the table, this would be a local max. So we have a positive D, a negative fxx. So let's just prove it. So positive D, negative fxx, so local max. And for the other problem, I'm just gonna write down what we had. So for this one, it would also be -36, 12 minus 0 squared is less than 0. You can plug the numbers in on your own. And since it's less than 0, we don't even need to worry about fxx. It would automatically be a saddle point. Likewise, we plug in -4, 0, and when we plug it in, we would get 36, -12, minus 0 squared. Once again, also less than 0, so we don't need to worry about fxx. It's automatically a saddle point. Okay, and next we do -4, 4, and when we plug everything in, we get 36 times 12 minus 0 squared, which is greater than 0, and our fxx is 36, which is greater than 0 again, so this is a local min. And that's all we need to do to solve this problem.